Hi, everyone. I think we're going to get started. So welcome to our IAC webinar series for May 2021. As a reminder, please change your name to your name, comma, your company or university. This just makes it easier during the Q&A if you have any questions. So a reminder to please keep your computer or phone muted throughout the webinar. The webinar will be roughly 40 minutes with a 15-minute Q&A. So if you have any questions, please save them until the end, or you can put them in the chat and we will address them at the end of the webinar. A quick mention for our upcoming webinar about specifying fans for industrial environments, which will be presented by AMCA. It'll be presented 2 Thursdays from now, May 20th at 3 p.m. On to today's webinar presented by Boise State University IAC about improving pump efficiency through the hydrophobic coating and impeller adjustment. We will have multiple student presenters as well as the assistant director presenting. I will now pass it over to you, Dev, to share your presentation.
Awesome. And actually, I'm going to start things off here. My name is Adam O'Keefe. I'm a graduate student here at the University of Idaho and a member of the IAC. Our office at the University of Idaho is a satellite office in conjunction with Boise State University. Working closely with them, we're able to cover, up to a region expanding into 4 states. We cover all of Idaho, Eastern Washington, Eastern Oregon, and parts of Western Montana. So working closely with them, we're able to cover a large area as members of the IAC, which we feel is very beneficial. So in the spirit of working closely with them, this project actually is in conjunction or builds off of previous research they had done at their office. And so that's what we'll be talking about today. And as Callie mentioned, it's looking at ways to improve pump efficiency through combination of impeller redesign and hydrophobic coating. So our team is a diverse group of engineering students and faculty coming from biological engineering and mechanical engineering and chemical engineering. And we've our roles extend to various parts of those disciplines. So anywhere from CAD design and 3D modeling to CFD analysis and simulation generation, as well as manufacturing a pump loop and then project support and data acquisition. And so these names here on the left are the ones that we'll be presenting today. Most of them have their cameras on, just so for your reference. So as I previously kind of mentioned, this builds on the base that BSU initially developed. So their concept was to look at increasing pump efficiency through decreasing the friction factor of their impeller and looking at how that affects pump performance. The original hypothesis was that applying this hydrophobic coating to an impeller will increase the efficiency. And through their analysis and development, they actually showed the opposite was true. So after they applied hydrophobic coating to the pump impeller, the reduction in friction actually reduced the efficiency of that pump performance, which is kind of a conundrum and left us kind of thinking that maybe there's ways to use hydrophobic coating, but still improve that pump efficiency. And so that comes primarily from the impeller redesign that we've started to present. Yeah, so the main objectives for this research was to quantify the pump performance change with an impeller redesign and hydrophobic coating. In order to do this, we felt the need to simulate performance of multiple custom impellers to deal with the angle change of those vanes and change the shape in the impeller, and then calculate those theoretical performances for those different designs, and then fabricate efficient impeller shapes and test the actual performance in an actual pump loop with various surface treatments to see how, in fact, hydrophobic coating and impeller redesign affects efficiency. And then to do those things, what kind of the key important methods we had to figure out and determine was what vein geometry to choose. So we had to calculate vein geometry with and without hydrophobic coating. So changes in friction and how that affects efficient vein geometries. Had to develop 3D printed models and impellers with 2 different materials to test those outcomes. Build a pump loop to test those in real time and acquire data for efficiency data manipulation. Create solid model of a pump casing impeller to run computational fluid dynamics simulations. And this is important in terms of validating our findings and providing further understanding to what is actually happening in the pump casing, and then compare those performance tests with numerical simulations.
So we started with this theoretical looking at the model of the pump itself. So what we looked at is what you're looking at, and the right image is the impeller vane that's in blue, and all the forces that a fluid will experience moving from the eye of this impeller to the perimeter. So there are couple of things here. If this vane was perfectly smooth or frictionless, it would not be able to push the fluid in any other direction than the perpendicular direction. So that was the premise of designing the most energy efficient impeller, that for a frictionless vane, it always has to push the fluid in the direction perpendicular to its surface. What you are looking at on the left side equation is the acceleration of a fluid that is moving from inside or center of this impeller to the perimeter. And as it moves, it experiences acceleration in 2 directions. Shown here as 2 unit vectors, UR, that is pointing in a radial direction, and U theta, which is pointing towards the tangential direction. And each component is given by this equation. And the combined acceleration in these 2 different directions is shown in a red arrow here as a combined acceleration. So since force equals to mass times acceleration, for the most efficient pump, the force has to apply in the same direction that fluid has to be accelerated to. And as I already said, for frictionless vane, only direction it can push is a perpendicular. So vane has to be perpendicular to the direction of the acceleration. However, for a real vane with some friction on it, so there are 2 competing forces. One is the frictional force, and another is the acceleration force. And now the vane angle has to be perpendicular to the resultant of these 2 forces, one coming from the friction and another coming from the acceleration. And we looked at this for a constant speed vane that is rotating at some angular speed of omega. And we also assume that there is no slip between the fluid and the vane itself for the most efficient pump. That means the fluid is rotating at the same angular velocity as the vane. Right. So of course, that acceleration is a function of velocity. And there are, again, 2 components of velocity. One is the tangential velocity, which is at any given radius is proportional to the speed of this vane. And then there is a radial velocity, which depends on the impeller profile and some other factors. And so depending on the flow and the impeller profile, how the velocity along the radial line changes varies a little bit. For this particular design, we assume that the velocity linearly changes from inlet to outlet. And for the velocity to change linearly from inlet to outlet, the profile itself has to be a little bit curvilinear on the top. From the measured data, and with the assumption that the fluid moving through this vane is incompressible, we were able to find the radial velocity and tangential velocity for any pump that we want to design. For this particular one, we actually measured the impeller the stock impeller that came with the pump, and calculate the velocity and acceleration for design flow and head. And you can see that the blue line is the acceleration, which is almost perpendicular to this vanes as it is rotating in a counterclockwise direction. And the red lines are for velocity. Although the magnitude of velocity itself increases as it moves radially, the tangential component somewhat decreases because from the continuity flow, as area increases on the outer surface of this impeller, velocity, the radial velocity has to decrease. So we put those equations into MATLAB, and we use a finite element approach to calculate the speed, that's velocity, acceleration, force, and all sorts of things as moves flow from inlet to outlet. We use this pump. This is a Dayton pump, standard low-cost pump that is rated for 3,500 RPM. And then pump itself can have a flow somewhere between 6 gallons per minute to 66 gallons per minute, and the head somewhere between 10 feet of water to about 80 feet of water. And according to the manual, pump manual, the pump operated most efficiently at around 50 gallons per minute, somewhere between 40 and 50 gallons per minute, and about 50 feet of head as well. So we put those into the model, and then we calculated the most efficient profile for this vane for 3,500 RPM with flow 50 gallons per minute and surface roughness for cast iron. And we also assume that the fluid is water at room temperature. We calculated the surface friction using the Reynolds number and Moody diagram equation iteratively for each of these finite elements to solve the whole model over time. As you can see, one thing that to point out is the yellow one is what the model gave, what should be the actual shape of this vane should be. When overlaid on the image of the impeller, that stock impeller itself, that was pretty close. So we are convinced that this is the right equation to use. Although there is a little bit of discrepancy in the middle, I think it's negligible. So we calculated this profile for the cast iron without coating, and also we calculated this profile with the coating. So when we sprayed with a hydrophobic coating, there was no easy way to find the surface roughness or friction factor for that surface. And since we assume that it's going to reduce, we just said, okay, let's look at the extreme case and assume zero friction with this hydrophobic coating. And this is what we saw as the impeller angle change from the actual to the modified. And we're taking this negative and positive angle as negative being the angle of attack at the outer periphery rotated counterclockwise, and positive is clockwise. So this is the same design for 3,500 RPM, same flow, no surface friction and the water. So to be honest, we were a little surprised that the angle change is just a little bit, 3.6 degrees. We were hoping that more angle change for frictionless surface, but looking at the equation and what's going on, it turns out that most of the force on the water is for acceleration, not from the friction. So friction plays just a little bit of the overall head loss, and most of the power is imparted as an acceleration.
And here you can see what the hydrophobic coating looked like on the impellers after it was tested. On the top of the slide, you can see both the stock cast iron impeller and the onyx nylon on the right side. And on the lower half, you can see how the hydrophobic coating sort of wore off after testing and underwent all the high pressure of pumping a high gallons per minute. And on the right side, you can really see how the hydrophobic coating rubbed off on the outer edge of the disc of the impeller. And to visualize what the hydrophobic coating does, there's a clip on the right. As you can see, it just kind of slides off the impeller a lot smoother than it normally would. And here it's kind of a comparison of the angles and of the change that we made on the impeller. On the left impeller, you can see just below these two reference lines on the top one, you can see how it's just a little bit below the line on the left side. And then in the middle one, that's our stock impeller. And on the right, it's a little bit above the reference line. And these are the three impellers that we actually 3D printed and tested on to see how the angle change would affect the efficiency of the pump. And for 3D printing, we actually printed both PLA and onyx nylon. The reason we use the onyx nylon was because it's a little stronger, and the 3D printer that we used to print was able to print in 100 micrometer layers. And so the disc on the impeller came out a lot smoother on the concentric circles as it went up, whereas the PLA ended up printing in 400 micrometer layers. So what we found after testing was that the onyx nylon impellers would fill up with water and then become a little bit more flexible, and then they would lose efficiency as they became flexible. Also another, oh, go ahead, sorry.
Yeah, so go ahead.
The onyx nylon also tends to have a lot less heat warping because of its high melting temperature. So when the prints would come out, we know that they would be a lot more exact than the PLA, which typically tends to warp through printing.
So on the data acquisition and testing side of things, this is the pump loop we constructed. So it's got two reservoir basins there for water, and those are primarily, well, they work together as a calibration system for this different sensors and data input. So we calibrated using both of them. But when we were testing, we would only run through one side of the pump loop. So only ran through one set of valves. The whole system is controlled through the VFD there on the right. It allows for precise control of what frequencies we want to run the motor at. There's a pump meter from SEL to monitor the pump, or the power meter through SEL that allows for the measure of power consumption over time. There's different sensors listed here, and a pump is on the bottom. So we monitor the pressure on both sides of the pump, the inlet and the outlet, so we get the pressure difference between the two or across the pump. There's a flow valve to monitor or restrict how much flow is going through the system, and then a flow sensor to monitor that flow. So a little more technical specs on what systems and instrumentation we used. We used a Dayton 3/4 horse self-priming centrifugal pump. The VFD is a WEG electric series micro drive VFD. In terms of data acquisition, we used a National Instruments DAC S series PCI 6143. This system has 8 analog inputs. It runs 16-bit and has 250,000 samples per second per channel. So of simultaneous sampling. So it allows for a wide range of data acquisition. Like I mentioned, there's the SEL power meter, the water pressure transducers, and then the water flow meter there. All these systems run in conjunction, and then data gets monitored real time by LabVIEW, and then gets exported at the duration of the experiment to Excel for data manipulation later.
So from the data we collected, we plotted this, we calculated the efficiency from how much power it is taking and what is the pressure difference in inlet and outlet and the flow, and plotted in this chart. Each point here is color coded. More greener the point, more efficient that point is. And you can see that this points are more greener in the middle and more redder on the outer peripheries. So these are less efficient and then more efficient. We also have this ISO efficiency lines to show the contour of equal efficiency. And this is the most we got is about 35% efficient. This efficiency is combination of both motor and the pump measured by the power meter. In x-axis, we have flow here, varying from mostly 10 to 60 gallons per minute, and head ranging from 10 feet to about 75 feet. One thing you might notice that the most efficient portion of this pump, unlike in a typical pump cut, is not at 100% of the speed. So 100% of the speed means VFD was set at 60 hertz, and then 92% would be VFD set at 55 hertz, 50 hertz, 45 hertz, and 40 hertz. So a couple of noticeable thing is the maximum efficiency occurred at around 83 to 75% of VFD speed. In most of this pump cut, as I said, the most efficient pump point would be at 100% speed. I think there are a couple of reasons that we could think that could happen. First, this is not just the pump efficiency, it is the combination of motor and pump efficiency. So that's one thing. The second one is we think the motor that came with pump is undersized. As we could tell, at 50 hertz, when motor is supposed to run at 3,500 RPM, that is the nameplate speed for full load motor, it was measured only 3,350 RPM. So that is the actual RPM. When we were running at 60 hertz at full load of about 60 feet of water head. So that's when the maximum power it was drawing, and it was overloading the motor almost 100%. So that may be another reason. And the third one is it is a low-cost motor pump assembly, and it's not designed for the best efficiency in mind. I mean, it is there could be some manufacturing variability, and the pump housing itself were not circular. It was the volute itself was more like a rectangular than a circular. So there are a couple of things that could have gone to get this pump efficiency curve. But in any case, this is the data that we're plotting, and this is how it looked like. So since our most efficient speed was not 60 hertz, it's around 50 hertz. So the subsequent comparisons were made for that particular efficiency. We do have a data with a similar trend, but all the comparisons are made for 50 hertz. So first thing we look at is the effect of material, if the material has any effect on the pump efficiency. And we are looking at three different materials. The cast iron is blue, gray is PLA, and orange is onyx. So I think this onyx, the cast iron and PLA probably would have the similar efficiency. But onyx is obviously far off, and that is probably because of how the onyx material got softer when it wetted in the water. Maybe the carbon fiber or the nylon absorbing the water and then swelling it, that makes it more rubbery and lost its stiffness. When it's dry, it's very stiff, but when it's wet, it's not that stiff. And that we think is the cause of low efficiency here. On the onyx side, you can see that efficiency is almost comparable in a low flow zone, but as flow increases, the efficiency decreases significantly. And we think that's because of the surface roughness. If you look at the surface, just the zoomed out image of these three materials, cast iron, PLA, and onyx, this 3D printed material is much more rougher than the cast iron itself. And that's what it is showing here. And it is consistent with all other speeds as well. As flow increases, the decrease in efficiency is significant. We looked at the coating, and the results we got was the same as what Boise State got in their previous experiment. The coated impellers had lower efficiency than the uncoated ones. That's true for cast iron, that's true for PLA, but that was not true for onyx. For onyx, coated had a higher efficiency than uncoated. And if we further looking into that one, we think that's because of when you coated an onyx material, it prevents water from getting absorbed into the material itself, and it maintains its stiffness. So that's why the coated material or coated onyx impeller is more efficient than the uncoated one. Although the relative magnitude of efficiency is much lower in onyx compared to the cast iron and PLA. So this is what we were looking at, the effect of impeller angle on efficiency. So we were able to do comparison only for the PLA because we tried to cast the aluminum cast the actual impeller, and we could not do that with great success. And onyx was failing because it's getting softer. So PLA was the only one that we looked at in the effect of impeller angle and efficiency. This 0 is as is, similar to the stock impeller, and then orange is +4 and the gray is -4. If you just look at and focus on this area, it will become clear that at this point, maybe +4 and -4 has about the same efficiency, which is lower than the 0 angle. And if the coating had reduced the efficiency, reduced the friction, then the orange impeller, which is +4, would have lower efficiency when it is coated. And the gray one, since that is -4, that's the model impeller, when coated, if it had the lower friction, it would move closer to the blue one. But if you look at this coated impeller, the opposite happened. The orange one moved closer to the blue one, that is +4 moved to the blue one, and the -4 moved away from it. So that could happen only for one reason, that actually coating the impeller did not reduce the friction, actually it increased the friction. So that was our conclusion from this test.
So in order to explain this, we first need to understand how the hydrophobic coating works. And the way that it works is it creates this air film layer. As you can see, it goes from this Wenzel contact area to this Cassie contact area, where it creates an air film between the solid and the liquid, which greatly reduces the friction. And it basically means that the liquid and solid are both contacting the air instead of each other. But it's been shown that under prolonged immersion or under high pressure, even when there's a hydrophobic coating, it will transition back into that Wenzel coating area. That air film will go away, and it will actually increase the friction to have a hydrophobic coating instead of decreasing the friction. So we wanted to verify this using computational fluid dynamics. So first we had to look at the pump geometry, and the pump we have actually has a rectangular cavity where the impeller is, which sort of created a question for us of what is the driving force of this pump. And we realized that it must be just creating a high pressure difference in the cavity instead of having a directional velocity if it was a circular cavity. So we know that the impeller must rotate to create that pressure difference. And we were going to attempt to validate this using computational fluid dynamics. So this shows our very simplified computational fluid dynamics analysis at 60 Hertz. And basically those velocity vectors show that the pump relies more on pressure than it does on a velocity direction of getting water to go in the inlet and out the outlet. And so if it had a more of a circular design of a classical centrifugal pump, then it sort of have an opening where all of the water gets shot out and it's more relying on velocity rather than a very high pressure, which helps us understand why the hydrophobic coating was reducing the efficiency. Basically, the pressure buildup was actually increasing the friction as it was shown before. And that explains, as you can see in the top, where the high pressure areas actually had the hydrophobic coating be worn off of them because of high friction.
So in the future, we need to have an exact surface roughness to be captured in our CFD work. It'd also be interesting to look at the different angles and planes in the CFD simulation itself. We'd also like to look at the efficiency improvement captured by applying a hydrophobic coating to only the low pressure areas, as well as improving the impeller geometry for the optimum efficiency depending on a new optimum operating point. So to sum up, we found that uniform hydrophobic coating reduces the pump efficiency and that the hydrophobic coating increases the fluid friction at high pressure zones, and that the impeller angle adjustment increases efficiency, but not really enough to make up for the additional friction loss due to the increased surface roughness. And so with that, I think we'll take questions.
Thank you for your presentation. So we're opening up for the Q&A. If you have a question, you can either unmute your mic and ask it, or you can put it in the chat and I will read it aloud.
Do you define efficiency as the hydraulic power divided by the electric power?
Correct.
Okay, and then the second question is on the impeller, the intake of the pump is in the middle, at the center of the rotation.
Yes, that's correct.
So and then it flows out to the periphery, right?
Yeah, so it doesn't look like from the picture itself, I think the pump picture, but if you look at the internal geometry, I think we have a pump image somewhere. This one. Yeah, so if just look at, this is inlet here and this is outlet. Although it doesn't look like it is at the center, there is a channel that goes and then enters from the center, and there is an impeller. This is a rectangular box, and there is some guiding vanes, and then it exits from the radially outside. Does that answer your question, Jim?
Yes.
Yeah.
Yes, thank you.
Sure.
All right, do you have other questions? All right, so I do have one for you. So do you think the hydrophobic coating would work on another type of impeller or pump?
We think that if it were to work on a different pump, it would need to be kept at a low pressure. And so not really that high of a capacity of gallons per minute, so that you would stay in the Cassie zone for friction instead of going to the Wenzel and creating more friction for the pump.
All right. So we have one from the chat. Are there plans to conduct similar research with a more traditional centrifugal pump with the circular housing and volute?
I think we will probably get the similar results because regardless of the volute shape, we still have this pressure gradient or high pressure area around the periphery. So we're still going to get into the Wengel zone, and then the friction is going to increase. Potentially what we probably will do as the future is just coat in the areas with a low friction, low pressure, mainly in the inlet side, and then see how it will improve the efficiency. And one other thing is, instead of coating with this hydrophobic coating in a high pressure zone, maybe some other materials like Teflon or something that with a low friction would be better suited. And that probably the next step in this research. This is a student, DOE sponsored student research. So if we get second round of funding for that, we probably can explore more towards that direction.
All right, another one from the chat. You showed impeller angles were designed for 3,500 RPM. How would the shape be different for other speeds?
Yeah, so that's a really good question. I think that's another big area of research. The impeller geometry change was more drastic than for different speed of impeller than for the hydrophobic coating. So hydrophobic coating, we just had about 4-degree change. If you change the impeller speed, the angle is as drastically different as 15 degrees. So given the fact that this pump actually does not operate on the field at design flow rate, most of these pumps are implemented or oversized just to satisfy the future growth or just to be on the safer side. There is a possibility that if we just change the impeller angle of those pumps that is running at lower speed to deliver lower flow, we can improve efficiency very significantly. So without even coating, I think there is a big need to change this angle for lower speed operation for the pump. If that answers your question.
All right, thanks. Do we have any other questions? All right, so if you want to enter your email in the chat, so in case anyone has any other questions, they can send them to you directly, or feel free to send them to me and I will forward them along. Thank you for your presentation.
Thank you.
Have a great day, everyone.
Thank you.
Yep.